Hello, my name is Kenza Mara, and I am presenting you towards a global species dataset by fusing remote sensing and citizen science data with graph neural networks. This is the work that I have done with David Dow and Björn Lutyens under the supervision of Professor Tom Crowther and Professor Seo Jung. This project was funded by Microsoft AI for Earth and WWF Switzerland. This work is part of a bigger project that aims to create a global map of our forests, gathering multi-scale information on trees coming from satellite images, drones, and citizen science. Santa Maria, Dow, and Lutyens have already developed TrueBranch. TrueBranch aims to verify the truthfulness of drone images via fusing and matching them with public satellite images. The research I will present to you today focuses on connecting information from remote sensing, namely drone data, to citizen science data. Today, we suffer from data scarcity on forests. We have already access to a large amount of data from drone imagery. Citizen science, such as smartphone images of landscapes or objects, could be widely used to enrich our global knowledge of the environment. However, there is no existing high-resolution labeled large-scale dataset on forests. This is why we offer a solution to leverage our understanding of biological landscapes and objects, like trees, by smartly combining mobile images to existing drone imagery. We are proposing the creation of a daily global dataset of biodiversity observations, just using citizen science and remote sensing data using deep learning. We use graph-based neural networks to fuse multi-view data. More precisely, our project relies on unsupervised learning with graph matching networks based on message passing with cross-graph attention used for link prediction. The graph matching networks must be robust against noise in GPS position, noise in drone resolution, missing data, and other obstacles inherent to the nature of the data. We expect stable mappings, that is to say, robust to the noise in the data. Fusing both sources of information has three main advantages. First, it will increase our knowledge of the forests. It will help inform automatically and quickly experts from forestry and ecology on the nature and specificities of each tree in a forest, without having to manually map corresponding images. Also, the widely available smartphone imagery that is regularly enriched by laypeople will considerably bring new pieces of information on biological landscapes. In our graph-based model, we model each detected tree by a node. Each node has its pair of coordinates, defined later as the two-dimensional node features. We consider two graphs, G1 and G2, containing the trees from drone images, and the other one containing the trees detected on mobile images. For each graph, we build edges connecting each node to its k nearest neighbors within the graph. Each edge has a weight or edge features defined as the inverse of the Euclidean distance between the two connected nodes. The goal is to find the correct mapping that connects the nodes from one aerial view graph to the nodes of the street view graph. Our approach is based on graph matching networks introduced by Lee in 2019. This type of networks computes the similarity score for a pair of graphs and also returns the cross-graph attention coefficients. We then deduce the optimal mapping of a pair of similar graphs using the Hungarian algorithm on the attention matrix output by the network. We have tested our method first on the Pasadena multi-view dataset built by NASA and Wegner and described in the paper GeoGraph Learning Graph-Based Multi-View Object Detection with geometric cues end-to-end. The Pasadena dataset provides labeled instances of different trees acquired in Pasadena, California. The dataset contains more than 6,000 individual tree instances from drone imagery and more than 25,000 annotated objects in the Street View dataset. We have tested our algorithm on pairs of subgraphs constructed from the Pasadena dataset. And from our preliminary results, we observed that our method is accurate and scalable. Namely, it can be used to map big graphs. We observed that similarity scores obtained are very accurate. For similar graphs, the computed distance is close to 0, while the distance between dissimilar graphs is large. So similarity for positive pairs is much higher than similarity for negative pairs. Now, focusing on similar graphs, we evaluate the quality of the matching. And the first and major observation is that the matching is much more accurate if we initially normalize the node features between 0 and 1. For graphs of 10 nodes each, for instance, accuracy is equal to 1 when coordinates are normalized, whereas it reaches only 0.6 with original latitudes and longitudes. We also observe that the accuracy slightly decreases with the size of the graphs. For big graphs, it is more likely to have some trees spatially very close, and for this reason to have them mixed up. Matching between graphs of 10 nodes is perfect with an accuracy of 1, but not perfect for graphs with 50 nodes, for which the accuracy is only equal to 0.86. To go further in our research, we will vary multiple parameters in graph matching network. We will also add additional node features such as tree species, bark type, or tree diameter if available. We would also like to try the graph-based supervised method GeoGraph and compare the results with the previous ones. Then we also look forward to try our method on different datasets to see if it generalizes well. And later on, we would like to scale up our method to build a global map of our forest. The long-term ideal goal would be to have an online available global map of our forests, gathering extensive amount of information on trees. For experts, it would be a quick and easy way to get up-to-date information on biodiversity. And this solution could, in the future, also be extended to other biological objects and landscapes. We are currently collecting mobile images of tree bark in the forest at Labor, Zurich, Switzerland. And we have, for the same forest, aerial images from a drone already available. I thank you for your attention. If you have any questions, add on to the research, or want to learn more about this project, do not hesitate to contact me by email. I'd be happy to discuss and share thoughts with you to make this project be a global concept. Thank you very much.